Welcome back. Today we're going to be talking about linear motion. Linear motion is the natural follow-on to Newton's first law. Remember we were talking about how in Newton's first law that if there's an unbalanced force, that means that something is going to move or it's going to take on a trajectory different from the one that it's already on. In other words, those things that are at rest tend to stay at rest, and those things that are in motion tend to stay at motion unless acted upon by an outside force. If it's acted upon by an outside force, usually it moves in a straight line, and that is exactly what Newton said in that first law. So we need to talk a little bit about linear motion. Here's a couple of examples I put here on the screen for you to just kind of look at really rapidly. Here we have a train moving down a track. Notice a nice straight track. A train of dogs here pulling a sled, presumably up in the Klondike or in the Arctic region. And of course, drag racers. One of my favorite pictures on the internet is this drag racing bus racing this truck here. And quite frankly, I don't know how that turned out for the bus, but it's pretty impressive that it's spinning those tires in the back so fast that the front has come up like this. So we're going to be introducing some really interesting mathematical tools, things that are going to be useful to you well past this class. And in any other science class, in many applications in life, you're going to be seeing almost all of these things over and over and over again. So you might want to grab a pen because you're going to be taking a few equations down. It's not to say that they're going to be that hard. Most of them only have a couple of variables in them. But with that said, make sure that you're ready to take these notes down. And don't worry, we'll do a recap at the end in case you missed anything. So when we talk about linear motion, we have to understand that linear motion is relative. The motion of objects is always described as relative to something else. For example, you walk on the road relative to Earth, right? But Earth is moving relative to the sun. So your motion relative to the sun is different from your motion relative to Earth. For example, if I'm walking down the street, I might be walking at a rate of, say, 1 meter per second, which is a nice stroll. However, I would not necessarily say that I'm moving at 1,600 kilometers per hour in a circle, but in fact I am, because the Earth is spinning at that velocity right where I happen to be located on planet Earth here on the big island of Hawaii as I record this at this time. So what number is the correct number? It depends on what I'm comparing it to. So if I'm walking down the street at 1 meter per second, it's relative to the street. However, it's also true to say that I'm traveling at 1,600 kilometers per hour, which is to say 1,000 miles per hour. Those of you that haven't gotten accustomed to the metric system, you definitely should. But at 1,000 miles per hour, I'm spinning on the Earth, and that's also true. And then there's actually also a velocity, an orbital velocity, as I'm screaming around the sun at a rate of 1 revolution every 365 days. So you can understand that we have to define our terms so that we know what we mean by motion, right? So it's relative to something. So the first thing that we need to talk about is this concept of speed. Speed is something that we've been accustomed to dealing with since we were kids. But have we ever really thought about what it really means? So probably not. We probably need to figure out what that means. So speed is defined as the distance covered per amount of travel time, right? So if you go say 2 miles, and you're able to do that 2 miles in 10 minutes, that's 2 miles per 10 minutes. That is a rate, that is a speed. However, in physics, we usually do units of meters per second, right? So this is where your ability to do unit conversions, just so you understand the meaning of some of these numbers, it comes in helpful. Speed is a scalar quantity. Remember in our discussion of Newton's second law, we got into the idea of scalar and vectors, meaning scalar numbers were numbers that just had magnitude, just some number associated with it, whereas a vector had not only a magnitude, but a direction as well. We need to keep that in mind as we go forward into this lecture, because we're going to be seeing vectors again by the end. Okay, in equation form, simply put, speed is just distance divided by time. Of course, we don't like to write distance every single time, so we just put d. So d is kind of the standard physics nomenclature for distance. And then t is almost always time in physics. So d over t is equal to speed. So if you happen to know the distance, you know the time, you can figure it out. So here's an example where they do exactly this. A girl runs 4 meters in 2 seconds. What is her speed? Plug and chug this, right? Speed equals distance over time. We take the 4 meters here and the 2 seconds there and plug them right into our handy dandy equation. And we reduce 4 over 2 to 2 over 1. 2 over 1 just reduces to 2. So the answer is 2 meters per second. And you could have done this in your head. But the main thing I want you to understand is that the equations aren't that difficult. It's a plug and chug operation. And it's something that you can almost kind of see coming a long ways away. So nothing to be intimidated by. At least nothing on the level of speed. Now there's different kinds of speed, right? There's instantaneous speed. We'll talk about this here. Instantaneous speed is the speed at any moment in time. So when you're looking at your odometer, this is an odometer that's in kilometers per hour. Incidentally, almost all cars in the world are in kilometers per hour. It's only in the United States generally that they report them in miles per hour. But if you want to know what 60 miles per hour is, it's actually, as I've lost my cursor, right here at about 100. It's about 100 miles per hour. So let's look at an example of what we mean by instantaneous speed. When you ride in your car, you may speed up and slow down with speed at any instant that is normally quite different than your average speed. In other words, you might be driving 100 kilometers an hour and then you see a cop. So you wind up going down to the speed limit, which say might be down here at 60. Okay, so your instantaneous speed of 100 is now 60 and then back up. So your average might be somewhere close to 100, but as you're going past that cop on the side of the road, you're doing the speed limit, you've dropped it. So your instantaneous speed is different. And so this is actually the number that is given by your speedometer, right? So your instantaneous speed is here. This is a neat car. It's got a full tank of gas and everything. So this would be one I'd like to drive. So let's go ahead and talk about average speed. Average speed is something that we look at when we're going very long distances, like on a road trip. So I actually took a picture of some people here from off the internet going on a road trip. It's basically the total distance covered divided by the total travel time. So it's basically still the distance divided by time, but this is instead of doing the distance or time and the moment like what you would see on the speedometer, you would do the total distance of the whole trip. So it doesn't indicate various instantaneous speeds along the way. In other words, the fact that there was a speed trap there and you slowed down, it wouldn't necessarily show up in your average speed. Okay, so average speed is just equal to total distance over total time. So for example, if you drive a distance of 200 kilometers, that's about 120 miles in 2 hours, and your average speed is therefore, well, it's just 200 divided by 2, 100 kilometers per hour. Makes sense, right? You could have done this in your head. So nothing to be afraid of so far. We've got 2 equations under our belt. Speed is distance over time, and average speed is total distance over total time. Pretty straightforward stuff. I would still write it down on my notes because we're going to add several more equations by the time this little presentation is done. So now we have velocity. And you might be thinking to yourself, velocity and speed, same thing, right? We actually in physics define it very differently. So velocity is a description of both the instantaneous speed of the object and the direction of travel. Whoa, wait a minute, we've got a speed and a direction. Oh, you can already kind of see where this is going. Velocity is a vector quantity. Remember, speed was a scalar. Velocity is a vector. It has magnitude, which is speed, and direction. So therefore, velocity can be restated as just being directed speed. And as a consequence, it has the same equation. It's distance over time, just like you would see for speed, except remember, we're going to call velocity a v, and then we're going to put a vector symbol, this arrow, right above our variable. And so it turns out that our equation is just v equals d over t. Remember, d is distance, time. Now, one thing that we need to remember from our pre-algebra, and some of you might not have gotten it until the earliest stages of your algebra curriculum, but usually it's taught in pre-algebra, is something called the change symbol, which is this delta right here. So physicists sometimes, and this should be sometimes all one word, but anyway, sometimes define velocity as a change in position over change in time. Okay, so this is basically a change in position is just a distance, right? So a change in position is usually if I've gone from here to here, that's a distance, very straightforward. So we can sometimes just write that as change in position over time, or which is just say change, the symbol is the change symbol, is what they call delta. Delta x over delta t. It's actually a change in time as well. And so what does that mean as opposed to d over t? What does delta x over delta t? It just means you take the final position and you subtract away the initial position. So the f and the I, that's final and initial. And you just divide it by the final time minus the initial time. And that will actually give you the velocity. Let me move the cursor out of the way. That will actually give you the velocity, is by looking at the change in distance over time. Very straightforward. Really, these two equations, so we've got two more tools that we can add to our little toolbox, our mathematical toolbox we'll be using for the rest of the semester. Very, very easy to use if you know what the notations mean. Don't get intimidated by symbols, right? By this arrow here. This is just a vector. It means that it's speed with direction. This just means a change in distance, or a change in position, or change in time, right? And we'll find ways that there's little tricks you can do to simplify things. But don't get intimidated by this. If you happen to know where you start and where you end, and when you started the clock and when you ended the clock, that all fits right in here and you get the velocity. Very straightforward. Before we leave this page here, I wanted to point out this man right here is just, he's doesn't have very high velocity. He's running in a certain direction, but there behind him are these bulls. This is from the Pamplona Running of the Bulls event in Spain that occurs, I believe, annually. And you'll notice that as this man is running from these bulls, he's taking a selfie of himself. And so I believe this picture, if I could remember when I found it on the internet, is called Idiot Running from the Bulls. Okay, let's talk about constant speed and constant velocity. So constant speed is steady speed, neither speeding up nor slowing down. Constant velocity, however, is a little different. So keep this in mind. Remember, speed is a scalar, so it doesn't care about direction. Velocity is a vector, right? So constant velocity is constant speed and constant direction, which is a straight line path with no acceleration. Now we're going to get into what acceleration is here very shortly. All right. So the motion, of course, is always relative to Earth unless otherwise stated. So fortunately, we don't have to worry about the Earth's rotation when we're describing these things. We can just simply give those velocities. And here we can see great examples of this, right? People coming straight down the road, all having a velocity in this direction, but any cars that would be going the opposite way, and you can see there's actually one back here in the background going away, it has a velocity in exactly the opposite magnitude. So if these are positive, that one that's going away is negative. These bike riders are all going the same direction. So you can see how this works out. Their speeds, however, might in fact all be exactly the same, because speed is a scalar, velocity is a vector. Just want to kind of reiterate that. So let's talk about acceleration. Acceleration is really the crux of what we want to talk about in this particular lecture, right? We've talked about acceleration a few times, but we haven't really gotten into what it means. Okay, first off, let's go back to our buddy Galileo that we were talking about during the first week. Actually, in lecture number 2, formulated by Galileo based on his experiments with inclined planes. Yep, there it is again. So what is acceleration? Acceleration is a rate at which velocity changes over time. So basically it involves a change in speed or a change in direction or both, right? So anything that is changing its speed, changing its direction, or doing both at the same time is accelerating, right? Because if you're going in this direction and you make a turn, some people are worried about the manner in which an acceleration occurs as you change in direction. As you change your direction, your velocity in this direction is going down, but it's increasing in this direction. That's the reason why acceleration is both a change in speed and a direction. This is a very important thing. Whereas if you were looking at the odometer as your car was making the turn, you could actually see that the speed doesn't change at all, but the direction does. So an example would be a car making a turn, or another example would be a man zorbing down a hill. So this is what they call a zorb ball. So here we have this nice grassy field, and there's a man actually inside this ball, and he's accelerating down into the valley just for fun. So you can all go zorbing at some point in the future to be able to figure out what Galileo meant by his inclined plane experiments. You can actually live it. All right, so let's put what acceleration actually is up on the board here. So in equation form, remember we kind of described it. Acceleration is a change in velocity divided by a change in time. Now remember, if it's going to be a change in velocity, that means velocity is a vector, right? We remember that velocity is a vector. So that means acceleration is also going to be a vector. So we would write A as acceleration with an arrow up on top. Okay? So that just means that acceleration is a vector. It's a change in velocity divided by the change in time it takes to make that change in velocity. And so we just get to use those really fun little symbols again, those deltas. So here's a delta V over delta T, the change in velocity divided by the change in time. And again, that's just the final velocity minus the initial velocity divided by the final time minus the initial time. If you have all four of these things, actually, you can solve the acceleration. And if you have the acceleration and you have three of these four, you can actually use a little bit of algebra and you could solve what the last thing is. Okay? These are skills that you should have acquired at least by the time you've taken a pre-algebra or finished a pre-algebra class. So the unit of acceleration is unit of velocity, and usually that's meters per second, divided by unit of time. So you might get something called, this weird unit like meters per second per second. That's pretty normal, actually. So let's look at this example. You are walking at 0.5 meters per second and decide to break into a jog of 2 meters per second. So you're speeding up. That's an acceleration, right? It takes you 3 seconds to get up to that speed. What was your rate of acceleration? What was acceleration here? It's a simple plug and chug. Here's A. We just know that A is equal to the change in velocity over the change in time. So here they are. Here's our final velocity, 2 meters per second, minus our initial velocity, which was 0.5 meters per second, divided by 3 seconds, right? Because it took us 3 seconds to finish it, minus our initial, which was 0. Our starting point was 0, presumably. So 2.0 meters per second minus 5 simplifies to 1.5 meters per second divided by 3 seconds. Okay, simple arithmetic here turns it into 0.5 meters per second, which then turns into this really interesting unit of 0.5 meters per second squared. All right, so it might be a little strange for you to think about that, but acceleration is a change in velocity. So that means that if something is accelerating at 0.5 meters per second squared, that means it's adding 0.5 meters per second to the previous velocity the previous second. So it means every second it's speeding up that much faster. Okay? It might take you a little bit of time to wrap that up in your brain. It's because it's not intuitive to think of it in those terms. And there's a reason why Galileo is so brilliant in being able to put that together. Acceleration was something that was missing from our scientific literature up until him. So anyways, think about that. 0.5 meters per second squared is the same thing as saying 0.5 meters per second, so added. So can acceleration be used to determine velocity? Of course it can, right? If velocity is a function of acceleration, then acceleration can also be a function of velocity. Let's talk about that. So we go back to our original equation, right? The vector of acceleration is just the change in velocity over the change in time, which is equal to delta v over delta t, which then turns into this nice thing. This is actually basically copied straight from one of the previous slides, if not the previous slide. So let's now assume that t initial and v initial equal 0, because they usually do, right? We usually don't like to assume that our velocity that we're measuring our acceleration from is going up and down, up and down. We usually just want to know from our endpoint and our beginning point what that acceleration was. So we usually just zero those out. It makes it real simple, right? So then we could just go ahead and plug those in. So if we're just going to assume that the initial time is time 0, right? Time 0 is going to be the beginning, and then the velocity is going to be 0 as well, our initial velocity. Look at this. We can plug those in, so it turns into v final minus 0, t final minus 0. Look at that. Anything minus 0 is just itself, so look, acceleration is equal to velocity divided by time. Now, if we want to put this, remember, we want to get this in terms of velocity. So we just simply have to multiply both sides by t, and voila. Velocity equals acceleration times time. And this is one of the most useful equations in physics, right? If you know the acceleration and you know how long it's enduring that acceleration, you can actually calculate its velocity at any given time. That's powerful, especially when we get into Newton's second law. So let's continue talking about Galileo, right? Remember him? So Galileo increased the inclination of inclined planes, right? Inclination means the angle, right? So here we see inclined planes of different angles. So steeper inclined planes resulted in greater accelerations, right? So this would fall straight down at a very high rate of acceleration. When the incline is vertical, acceleration is at maximum, the same as that of a falling object. In other words, this basically is falling with nothing underneath it. There's no wood block or no inclined plane to keep it from going straight down. It's basically being pulled straight down. So when air resistance is negligible, all objects fall with the same unchanging acceleration. Right? So this is one of the things that Galileo observed, is that all things tend to hit the ground at about the same time. When we get to the chapter on gravity, we'll find that this statement is not exactly true, but it is mostly true. All right, and the amount of difference between falling objects on Earth is very, 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 very small, almost unmeasurable, and certainly not to the naked eye. So I just want you to be aware that there might be some modification of some of the things that Galileo had observed, especially when a guy named Einstein started looking at some of these problems. All right, so if something is falling off of an inclined plane, but the inclined plane is straight up and down, we would just say it's basically free falling, right? There's nothing underneath it to stop it. So free fall is really just falling under the influence of gravity only, with no air resistance. Freely falling objects on Earth accelerate at a rate of 10 meters per second squared, or 10 meters per second, right? That's how we could say that. That is 10 meters per second squared. Now the more precise number is actually 9.8 meters per second squared, but when you're doing the homework, you'll find that the acceleration due to gravity at 9.8 meters per second squared or 10 meters per second squared, we're not going to care, right? We're really only interested in being able to talk about the concepts, right? This isn't going to be a math class or a physics class that is completely riddled with mathematics. We're just really looking at the tools. So in this case, we know that the acceleration of gravity from Earth, remember, A is a vector, right? We cannot forget that A is a vector, acceleration is a vector. So the acceleration due to gravity is 9.8 meters per second squared, which is about 10 meters per second squared. This makes our calculations really easy if we just round it to 10. You'll see me use them both, but frequently 10 will be the number that I will use. And the symbol we use to talk about gravity is usually not A, gravity. We usually just give it the symbol G. So this is an important thing to keep in mind in future chapters, especially in Newton's second law, that g is gravity. And it's also a vector because it's an acceleration. So let's go ahead and use one of our tools, free fall. How fast is something falling? The velocity acquired by an object starting from rest is, remember this equation, velocity equals acceleration times time. We derived that. Velocity equals acceleration times time. So under free fall, when acceleration is 10 meters per second squared, right, because we're going to round it to 10, the speed is, well, it's acceleration times time. So the acceleration is 10, time is 1, so you'd expect it to be 10 meters per second. So yes, it is 10 meters per second squared after 1 second. What about after 3 seconds? Well, we just take the 3, we multiply it by the 10 meters per second squared, and it turns into 30 meters per second, and so on. So it's a very straightforward relationship that velocity and acceleration have. And of course, if we want to get back our old relationship of what acceleration is, we just divide both sides by time, and acceleration equals velocity divided by time. This is exactly what we've been saying since the beginning of this lecture. So we're right back kind of making full circle to this concept of speed, velocity, and acceleration. And notice that they're all in a straight line. The moment we start to curve something, it's a little bit more complicated. We're going to get to those a little bit later, but they're also very fun, okay? But we still have a few more things to learn before we get to curved paths. So with that said, I want to go ahead and complete the lecture here by just reiterating what those equations are that we went through in this lecture, right? Including one that I didn't derive in the lecture, but you can actually see it. And I don't think I needed to actually go over it, but I have it here nonetheless. Okay, remember, speed is distance divided by time. Average speed is total distance over total time. Velocity is distance over time, but remember, this is directional velocity, right? This is a vector as opposed to speed, which is not. Velocity can also be written as a change in position over time, or delta x over delta t, which equals x final minus x initial, divided by t final minus t initial. Okay. Our really useful equation that we derived a little bit earlier is velocity equals acceleration times time. We showed how you can use that to predict things like, if you're falling in a gravity field at 10 meters per second, what would be your velocity after 5 seconds? It's very easy because I just know to multiply 5 seconds times 10 and I get 50. I'm going to be traveling at 50 meters per second. All right. This is an important relationship to know, that the acceleration due to gravity is 9.8 meters per second squared, which is about 10 meters per second. That's a totally close enough approximation for us. We're totally happy with that. The acceleration of gravity is usually called g. And this is the one that I didn't show you, right? But you can see it over here, that it's really just a rewriting of this. And this is just distance equals velocity times time. So we can see that, multiply both sides by t. Distance at that time would equal distance equals velocity times time. So this is where this comes from. And then, of course, the acceleration equation, which is change in velocity divided by the change in time, or delta v over delta t, or v final minus v initial over t final minus t initial. So I went over all that. I know it might be a little tedious, but I think it's important that you have, at least in your notebook, some of the more important equations written here, because they are really useful to have on hand when you're going through your homework sets and you want to be able to look something up really, really fast. I hope you enjoyed us going over these little math tools. They're really useful. We're going to be using them a lot. We're not going to be doing too many of these types of calculations, but these will be fairly common. Okay, so the ability to calculate velocity, speed, things like this are things that you definitely need to be able to do. Okay, velocity equaling acceleration times time is one of the most important equations in physics, so you will need to know that. Make sure you have it written down, and good luck on the homework assignment that is currently posted. If you have any questions, as always, send me an email.